Hey guys, this is going to be my video on topological sort and heap sort for UPE. So the first uh, question that I had to solve was checking to see if it was possible to take a list of classes given the prerequisites for each class. These prerequisites basically represent edges in a directed graph where each course is a node in your graph. And if you can take all the courses, that means that this would be an acyclic directed graph. There are no cycles. If there's a cycle, then that means that one prerequisite is like they're dependent on one another, and therefore you can take none of the classes that you need to take. Um, so just an example of what topological sort is. Basically, topological sort, you're going to take a directed graph, and if you're going to create a ordering to them. So for example, here you have a directed graph where basically directed graph means each edge you can only go one way. So they're like there's arrows on them, they're directed. And a topological ordering is basically your arrows only point forward. So for example, here 0 can be placed here because there's nothing that will have to point back to 0. There's no edges going into 0. So the way that you construct the topological ordering is basically you have to keep track of how many edges are pointing into your node, and if there's 0 edges pointing into your node, then it is safe to add that edge to the ordering because at that point there's no edges that are going to be pointing back. So for this, if we run through the algorithm, when you go through, you notice that both 0 and 6 have no edges pointing into them, so therefore it's okay to choose either one to place as your first one. This one chose to place 0 first. And then after you place 0, you can keep track of the number of edges that are pointing into like 1 and 2. You decrease them by 1 because these edges are no longer relevant. They'll be pointing forward now. And then they'll place 6, and then once these two edges are gone, you notice that the number of edges pointing into 1 is 0. So now you can add 1, and then these two edges are gone, so you can add 5, then 4, then 2, then 3. There can be multiple topological orderings, and that just simply means that, if there is one topological ordering, then your graph is acyclic. So I'll now just simply go over how I implemented this. I made a dictionary to keep track of this dictionary is going to have an array for each node, and it's going to keep track of the edges that point in. And then your edge count is basically going to count how many edges are pointing into it. So once your edge count, like an indice of your edge count, becomes 0, then it's safe to add that to your ordering. So these first two for loops here are just to initialize both of these. So you're going to go through every single course, and I'm just creating a dictionary element for each of these. And then afterwards, for every single edge in your list of edges, you're going to first add the prerequisite to your edge list, and then you're going to increase the count by 1. And then this 0 is going to be your set of like possible nodes that you can now pull from. And you're going to go through that. If anything equals 0, then you're going to add it to 0. And then from then, every single course, you want to add it to your topological ordering if possible. If there's no courses to add, then that means that it failed, and therefore you're going to return an empty array because it's impossible to take all the classes. Otherwise, you're going to pop any course out of that 0 set. You're going to add it to your topological ordering, and then you're going to decrease the edge count for the edges that it points, or the nodes that it points to. And at the very end, you're going to return the ordering that you get. And if we run this, you see that it works. The second algorithm that we go through is the heap sort. For the heap sort, basically you're constructing like either a min heap or a max heap. And what these heaps are is it makes it really easy to find the biggest element or the smallest element. And the way that they're set up is it's a tree, and it's a binary tree. and every single child is always, for a max heap, every single child is always less than its parent node. So it's like basically strictly decreasing. And for a min heap, every single child node is larger than its parent node. This can be represented in an array, just because it's very easy to find the children and the parents just from the indices. Um, so you don't actually have to construct a tree. You can just represent it in an array. Yeah, the insertion is log n time, and just finding the min elements really fast. It's O of 1. Yeah, so this can prove to be a very helpful algorithm.